online. So we would like to start now the session on hybrid quantum classical computing. We introduced the topic on quantum computing in IGARSS because this is opening new perspective mainly for the high complexity problem we have, and also in the near future probably for the big data. Give now the floor to Gabriele Cavallaro presenting the first presentation.
Yeah, thank you very much, for the introduction. Welcome to our session. Very happy to be here in person, be able to touch some physical atmosphere. Yes, I'm Gabriele Cavallaro, and I'm from the Jülich Supercomputing Centre, where I lead the Simulation and Data Lab, and I'm also an adjunct associate professor at the University of Iceland. So the idea of today is to give you a presentation where we will go through different steps. We'll start by looking from the perspective of Earth observation, moving through some, interesting milestone and step that happen in quantum computing. Finally, moving more and describing you a bit what are the activities that we conduct at the Jülich Supercomputing Centre, where we try to really connect the world of quantum computing and high performance computing, so supercomputing. Very nice. Welcome. Okay, and then at the end, I will give you some, a snapshot of activities that we conduct in the Geoscience and Remote Sensing Society. Okay, so let's start. So now, if we look at what is going on in the Earth observation, especially in the Earth observation market, we have seen that there is a rapid growing, right? So this is thanks to the technical breakthrough regarding data collection, and there is an increasing offer of high quality Earth observation data. This both in terms of variety of sources and also, of course, quality, increasing quality of resolution. Now, of course, if it was like, some time ago, I would probably start by defining, as usual, Earth observation are the big data, right, with the P definition, value, volume, veracity, etc. Of course, this is true, and we know that Earth observation data, check all these boxes, of course, but also we know that Earth observation data are more highly, let's say, we can be described in a way that goes beyond even the big data definition. For instance, we know very well that data could be high dimensional, and this usually because data reflect complex relationship, for instance, between natural and social phenomenon, which is, of course, have nice correlation, but also multiple data attributes. Then, of course, we know that AO data are very complex. Data usually is incorporated in highly complex data models, and where we know what calculation include data processing, analysis, and modeling between complex systems. Then, of course, we have also the high uncertainty, and this is due to the fact that data errors and incompleteness data is unavoidable. And this is due to the high not reliability during the processing, during the acquisition process. So to summarize, there is an enormous volume of raw data to analyze for scientific research and commercial use, meaning that any improvement in the underlying algorithms, could unlock new large value and information. So if we take a step back a bit, and let's come back a bit to history, and let's consider and let's answer the question, what is classical computing? So if we look a bit at the timeline of physics, we know that before 1900, this is the period of classical physics, and after 1900, we have the quantum modern physics, and this includes the general relativity and quantum physics. Now, the term of classical in classical computing is not related to the pre-era of physics, but it is just a term to distinguish classical computation from quantum computation. Okay, so just to be clear, the term classical was adopted firstly by quantum physics. So if we look at the revolution that happened in the quantum world, we could define two regions. So we have the first quantum revolution, where basically we know that the computation is a physical process, so it is governed by rules of the physics world, which is quantum, right? So these include transistors, for instance, which were invented in 1947. which use, for instance, the tunnel effect, and are the basis of our existing digital world. We know that. Now, component in quantum and computing devices like your smartphones and classical computers, right, are small enough that quantum mechanics plays an important role in how they were engineered. So, to be clear, right? So, classical computers also use the properties of quantum mechanics, semiconductor transistors, as the physical process involves microscopic particles like electrons, atoms, and circuits, and molecules, sorry. However, we can describe them with the microscope classical theory of electrical properties of circuits. So we describe them from the high level, okay? In the second phase, in the second quantum revolution, what happened is that finally now we have technologies which have the ability to control individual quantum objects, photons, atoms, electrons. And in this case, in these technologies, we use quantum superposition and entanglement properties. So if we look now the history from 1980 to today, basically, we can see that there's a lot of milestone and interesting step happened. So of course, we start from the very beginning of 1980, where there were already conceiving concept and theoretical basis for quantum computing. Then moving along, the first quantum algorithms appear, Shor, Grover, they're very famous. And then slowly we started to see the first quantum computers, of course, with very small amount of qubits. Finally, then we see a race where people try to really increase the number of qubits, finally arriving in 2011, where we had the first commercial quantum device, which is the D-Wave, the wave annealer. So, of course, then the quantum world started to merge also with other research fields, artificial intelligence. So that's why now we started to have also from 2010, the rise of quantum machine learning. And nowadays, 2020, we are in the area of noisy intermediate scale quantum era, and where we have computers that goes beyond 50 qubits. Okay, so, and in this case, in this moment, there is a race in terms of technology. What is the right technology to use to control qubits? And there are many available, many there. And of course, now we are here wondering ourselves if also quantum computing could be something useful for our community in Earth observation. We will have to identify what are the possibilities, what are the processing steps inside our workflow, Earth observation workflow, that could benefit from quantum computing. And this is our responsibility to identify this. So let's again give a proper definition of what is a quantum computer. So a quantum computer is a device that exploits explicitly quantum mechanics, of course, for matter of to do calculation, to do computation. And this means that we use essential properties that cannot be explained classically. And we are talking about superposition, entanglement, interference, non-locality, duality, etc. So quantum computers are not fast computers, but computers that operate in a different way. This has to be clear. These are not just fast computers, they are, but also they compute in a complete different paradigm, okay? So, which can only be described with the law of quantum theory. So they use basically microscopic systems such as photons, electrons, atoms to process directly the information. That's what they do. So we know that quantum technology, we are realizing that they are very disruptive. And here I present you the main 4 pillars where quantum computing is actually quantum technologies actually are making breakthrough. So we can consider one by one. So quantum communication is basically the application of quantum physics closely related to quantum information processing and quantum teleportation. So for instance, this can be used for, for protecting information channels, like, with quantum cryptography. Then we have quantum sensing imaging, I think very relevant for our community. And in this case, the idea is to engineering of quantum sources and quantum measurement that are able to beat current limits of sensor technology. And here I'm talking about, for instance, quantum microscope, quantum radar, quantum telescope, so very interesting topics. Then, of course, we have quantum simulation, also very relevant nowadays, where the study of quantum system is done in a programmable fashion. And in this instance, simulators are basically special purpose devices designed to provide insight about specific physical problems. And here I'm talking about, for instance, quantum chemistry, material science, design of highly efficient battery, etc. Then, of course, we have quantum computation, obviously, which, of course, it is about solving challenging problems faster and better than a classical computer. Image intelligence factorization, etc. Okay. So if we look a bit at the market, we know that the current computing quantum technology allow to solve only small size problem. Okay, so and most researchers believe that before we get a full tolerant quantum computer, it will take some time. However, we have seen that there has been a boom in the market and investment, especially a lot of money put there in the market for quantum technologies. So let's start by considering, for instance, governments that have launched large research programs on quantum technology. In Europe, for instance, we had the European Quantum Flagship Initiative, which is basically summing up to several billion euros of public funding. The Chinese program, for instance, which includes the launch of a satellite and the installment of a quantum key distribution link between Beijing and Shanghai. Very interesting also application. At the same time, of course, large multinational companies like Google, IBM, Intel, Microsoft, Toshiba, you name it, had also invested a lot of money. Also, in the meantime, we have also startup companies who were established during the last decade. So you see that everything is happening very fast. And if we just, here is just a graph from the Boston Consulting Group that estimate that basically quantum computing could create a value between 450 to 850 billion, okay, in the next 15 to 30 years. So basically, if we now put together the growing of the Earth observation market with the booming growing of the quantum computing market, it is clear that we need to have to really establish a way find out if quantum computing could really be something that could change how we process data also in Earth observation. Okay, so let's now enter a bit into quantum computing for real. Of course, there are many open questions in quantum computing in general, and I think I already kind of mentioned them. However, we need to find out how quantum computing could bring an advantage also in Earth observation, science, and applications. Basically, we need to really find out if we could really have in our processing workflow moment or like processing step where we could get an advantage, and not only in time to solution. It's very relevant could be also to find, for instance, processing step where we can get an advantage in the energy consumption, which is very relevant nowadays, right? And also in this paradigm, we strongly believe that, especially what in our research center, that this could be only achieved by in a situation where you have hybrid computation between classical computing and quantum computing, so not just purely quantum computing. So, in fact, also at the European Space Agency, we know that the European Space Agency actually is already investing in a way and by providing money to projects that try to address this kind of question. Here I see 3 early project that started, and I will highlight the project where I'm involved with the Jülich Supercomputing Centre, and here exactly we try to find out if we can find an interesting workflow that can really work between supercomputers and quantum computing for addressing large-scale Earth observation problem. So here on top you see some of the objectives. And you see that in the second point, we will use the so-called Jülich UNified Infrastructure for quantum computing, I will explain it very well what it is in the next slides, where basically we can try to really integrate these two worlds of high-performance computing and quantum computing in a modular way, and it will become clear. We have already done some work, especially by considering classical machine learning. For instance, support vector machine, support vector regression. Here you see, for instance, an example of what you would get out of a classification problem with 1 versus 1 from scikit-learn, typical SVM implementation, and with quantum annealer by using an implementation of a multi-class support vector machine that we did. So you see, this is a proof of concept. It is working. We get something comparable, which is already, is already good enough. And of course, the next step would be to identify what is the real gain to use this technology. Okay, now I want to talk about the modular supercomputing, which is basically a computing environment that integrates heterogeneous HPC systems. And this can include different types of accelerators, GPUs, FPGAs, but of course also more innovative quantum computing technologies, like for instance, quantum computing or neuromorphic computing or anything else that we are going to get in the future. It is very important to notice that this MSA is modularized by its software stack, meaning that from the user perspective is kind of going to be, it is a single system where everything is integrated in a single software stack. So this is what we are actually working a lot in the Jülich, and of course the final objective, the very futuristic objective would be that whenever you as a user, you will have a processing workflow, which each user has a different processing workflow, meaning that each processing step is different, meaning that each processing workflow will need a particular supercomputer, right? Because each processing step will have particular requirements. And the idea is that in the future, this kind of system will be able to create your own supercomputer by directly providing it and making your own, let's say, setup of modules. Of course, this is the future. Nowadays, you still have to, of course, decide and offload the different computation and the different modules, but this is a very, let's say, important. So an example of modular supercomputing is our latest supercomputer, the Jülich Wizard for European Leadership Science. It is a multi-flop modular supercomputer capable of 85 petaflops, and this is basically equivalent to, let's say, more than a computing power of 300,000, let's say, modern computers. You could see that actually this was in 2020, the first in Europe and also 7th in the world. So this is a modular supercomputer, and it is designed for simulation and also large-scale machine learning. It will become clear why I also am presenting this, our supercomputer. So at JC, we are now in the path, Europe is in the path, the world is in the path of getting to exascale. We had already a nice milestone lately, but in Europe, we are now moving also forward, and that this is actually our timeline at the Jülich Supercomputing Centre. We had many projects before we could actually start to think about exascale. There's a lot of projects related to how you design the hardware, the software stack, the applications. So it's a long path you see from 2011 with our first deep projects, arriving now to find the possibility to install in our research center the first exascale supercomputer in 2023, 2024. So this is a recent news a few weeks ago. Okay, so why I'm talking too much about this? Because in this kind of computing environments, we can really aim at using and producing workflow that are using hybrid workflow that use exactly different type of modules, right? So this is exactly what we have here and what we try to achieve. Again, our statement or policy idea, if you want, is that exactly we know that to achieve exascale supercomputing, we know that we will have to merge the forces between HPC and quantum computing. So not having silos of different computing technology, but join them together. So let me talk about finally, which is finally the let's say the result, or like what I try to aim in the title. So this is exactly what we are doing in Jülich. So we are building a European quantum computer user facility, which is called JUNIQ. And JUNIQ provides access to many available quantum simulators and devices at different levels of technological maturity through a very user-friendly programming platform, even by using Jupyter Notebook. So at this moment, what it includes is the Wave quantum annealer, and I will come back this to later, but also 2 quantum emulators that are basically software to simulate quantum computing devices. The first one we have is the Jülich Universal Quantum Computing Simulator, and the second one is the Atos Quantum Learning Machine. Soon, what we're going to have is a quantum computer developed in the European flagship project Open SuperQ, which is basically a quantum computer with up to 100 superconducting qubits. Also, we're going to have quantum computers coming from national German programs. So it is very important to remember that providing access to quantum to machines is not sufficient. We know this very well from the world of high-performance computing. Providing is not enough. We also need to provide support and software and tools, and exactly what we're also doing in JUNIQ. JUNIQ works on the development of algorithms, prototyping application, but also providing courses, training, material, because otherwise, if there is no communication with the user, with the scientific community, there is no way that this system will be useful, right? So finally, you see on the left side the new building of our quantum annealer. It looks, nothing special, but actually there is a lot of technology inside this building. You can imagine that these computers are very sensitive to vibration, for instance, and many other effects. So the technology inside this building is quite impressive. And of course, also it's impressive what is inside, which is a quantum annealer from the D-Wave system with more than 5,000 qubits, and which we are already using. We are already providing access through program where you basically need to submit proposals. If you have an idea, if you have a project, you just submit a proposal and you will get hopefully computing time if your idea is good and can really exploit quantum annealing. Very interesting, also coming soon, is also again in the context of unique and hybrid quantum classical computing. The Forschung Center in Jülich is coordinating the European project High Performance Computing Quantum Simulator Hybrid, HPCQS, which aims at developing the cloud-based European federated infrastructure. So what it's going to do is going to integrate two quantum computers with more than 100 qubits into HPC systems in Europe. The first one is the Hewlett-Curie HPC system at Jülich in France. And the second one is will be connected to the Jewel system that I also showed you before. So this is not a random system, but the project ran actually in a campaign to find out what could be let's say, the most approachable or the most suitable quantum computing to connect, and this was selected by the company Pascal, which is basically a Fresnel analog quantum simulator. There will be one simulator in Jülich, Germany, and one simulator in France. So two quantum computers, quantum simulator. Okay, so that would be very interesting things to wait for, especially also for users. So now I would like to conclude my presentation by telling you a bit more about what is going on in the Geoscience Remote Sensing Society. In particular, 2 years ago, we established a new working group called High Performance and Disrupted Computing in Remote Sensing. This is under the umbrella of the Earth Science Informatics Technical Committee. And the idea here is really we want to connect as much as possible users in GRSS and beyond that work at the intersection of using computing technologies for solving remote sensing applications. And so this was born 2 years ago, but actually I believe we did already a lot. Firstly, by establishing a new summer school. It happened already 2 times. This is from actually months ago, and where we had the final in-person summer school at the University of Iceland. And you see here many logos, so many contributors. So if you go at the link here, you will find that there is a website under the GRSS website where you find the videos of all the lectures, the teaching material slides. So feel free to really have a look. But why I'm talking about this, because of course we had a very interesting also input from the quantum computing technologies. On the left side, you see contribution from the European Space Agency. Ventrale So actually presented the initiative that they are actually currently doing at this European Space Agency. And on the right side, you see a full day actually lecture from Piotr Gravron from AstroCen, which actually present also quantum computing for Earth observation. So please feel free to have a look to this. We also recently published a magazine, and here in this magazine we present basically the different computing technologies and how they've been applied in the last decades or many years, let's say, to remote sensing applications. So it's a nice also overview to see how the different technologies, including quantum computing, have been developed in the last period. So feel free to also have a look. And of course, this is also an activity of the working group. So we are here in this session. So it's also another activity that we are promoting, of course, with me, Mihai, and other at our chairs. So you have a nice, interesting program for the next presentation, but also don't forget that on Wednesday we will have another session, right, on harnessing the power of quantum computing for machine learning. So if you're interested in this topic, please also feel free to come to visit us there. Of course, if you're interested to join us, to help us, to promote new activities, feel free to join us. Just go to the website and click the button. Finally, if you're actually already working on quantum computing, so remember we actually should be still open, right? So
yes.
Very
yes,
good. Yes. So we have a special issue on the on JSTAR. So each contribution is very welcome. Please feel free to submit. Thank you for your attention.
Thank you, Gabriele. Thank you for generating an entanglement in between Earth observation and quantum computing. If there are questions, also questions from our remote attendees. I start myself, if there is no question, so remote. If you can give a hint, because that is a short question with a long answer, just to present the, in 1 minute, the European landscape in terms of quantum computing relative to European Commission and ESA.
Yes, so as I mentioned, ESA is already pushing a lot in this direction. In fact, these are, for instance, an example of project that, the one that I was showing before. So these are projects that try to really to tackle these problems. There have been other calls, let's say, for activities. In fact, there is a lot of the community is moving a lot around. And of course, there are many projects, national projects, a lot many national projects, different European countries. But of course, the project that I presented, HPC, US, for instance, and Open SuperQ are very important in the world of connecting really. And I think for us in observation, it's important to have this connection because we have really complex problems, large problems. We cannot aim at really try to solve all our problems through technology, at least nowadays, right? Maybe in the future. So that would be.
Thank you. Thank you very much.
Yeah.
Still time for a short question with a short answer.
I have a question. So
thank you very much.
I'm
very
Manish.
And in the slides, I found that some open questions, probably. What is the main contribution? What can be the main contribution of quantum computing to Earth observation community or something like that? I'd like to know your present answers or your present direction.
In terms of exactly where to find the advantage. So, I mean, the point is that we need to make sure that the communities talk to each other, right? The quantum computing community has to make sure that communicate also with the community of Earth observation in order to find out what are the problems. Of course, it's also our responsibility here to find out if you have a workflow, right? You will know which are the process steps that are more complex, and this has to be an information that has to be with the producer of quantum technology, for instance, or HPC, in order to be able to find the right compromise. This is what we call co-design. The different communities need to talk to each other in order to find a solution. And I believe that in the next 5 to 10 years, this has to establish a lot. And this is not just true for Earth observation, but all other communities. Because in our case, things are not so straightforward. For instance, as chemistry, material science, there is more clear, more or less, what could be the advantage. But in Earth observation is a different beast. So we will have to see.
So in particular, in this community, well, do you have any idea to make it specialized or
Not sure. Maybe Miai, you have an answer for this?
I need to hurry. I try to answer in a very simple way, and later maybe I can explain longer because I don't want to delay the next presentation. So the bit, the classical bit Shannon, as a measure of information, it's anything. I mean, it can be a coin or a piece of wood, anything which can be flipped in between 0 and 1 or 2 states, doesn't matter. The qubit, it is physical.